Welcome back, and today we're going to talk about constant acceleration kinematics. We're going to look at how stuff moves. You may have seen these formulas before. They are your constant acceleration formulas. You can use them when A, that's right, is constant. What we're going to do is we're going to show you how to get these. You can get them with calculus. We'll show you a little bit graphically just so you have a little bit different approach, and then we'll work a couple examples. So looking at this, let's start here. Acceleration is constant, it's a line. I want a formula for velocity, or change in velocity. I just want the area. What shape is that? It's a rectangle, so delta V is just AT. Boom, now I have this other shape for velocity. So I want to look at change in position, the area under this curve. So I'm going to start here. That's a rectangle. It starts at some initial velocity. So that's V naught, or V initial, times T. Plus, now I've got this little piece right here, this triangle. It goes from V final to V initial. So that's triangle area, V final minus V initial, it's a minus sign, times T, where if I plug in this from before, from that last little piece, this is A, and I wind up with my final, delta x equals V initial times T plus 1 over half A T squared. You can get it from calculus. This is just a visual way of looking at it with some shapes. Give you a little different flavor. Now let's work some problems. First, I want to draw your attention to this little area over here. I always like to make a box. Write down everything you know. That way you can pick the best formula, so you're not just floating around in the dark. In this case, we have a car. Also draw a picture. That's a car. It's going. So we're going to arrange for the variable we want to solve for, in this case, time. I also recommend work with variables first. If you make a mistake with variables, it is much easier to find. Plus, you don't just plug things willy-nilly into your calculator and hope everything works out. Then, after we've solved for it, we can plug it in and get change in time is equal to 5 seconds. So that was a car accelerating constant rate. Here we are. Car starts at rest. Ooh, also, tricky word. Rest, V equals 0. I am conspicuously missing time, and therefore, I'm going to pick the formula that doesn't have time, based on what I know. This formula is just a conglomeration of the other two that we showed. Again, solve for variables first, then you plug in your numbers, and delta x is 2 meters. Remember, meters, very important. You have to have a unit. One more question. Constant acceleration while the distance is 16 meters in 4 seconds. So now I know delta x. Same type of thing, except now I have time. Well, what can I do with this? If I start here, I can get v squared is 2a delta x. Fine. And now I know acceleration. Oh, look, I've got this formula for acceleration. I know using this formula, and I can combine them. I can just mix and match. You can put pieces together. Vi is equal to 0, which gives you your final expression for your final velocity, delta x over 2 delta t. And then, only then, after we've rearranged everything, then we can plug in the numbers and get V final is 2 meters per second. Pay very attention. All of these units need to match. These units need to match these units. If they don't, it's a sanity check. Something's wrong. Go back and check. We're going to take a moment to talk about average acceleration. Average acceleration is also a constant acceleration. If your acceleration is the same, it's not going to change depending on when you look at it. So let's say we have the acceleration object. Ooh, we've got a function of time. I want to find velocity. What's the relationship? Well, a equals dv dt. We're going to look at another integral. All right, so we plug in our definition for acceleration, move this dt over to this side, and integrate, just like we've always done. Start at rest again, and at time equals 0. You can start at whatever time. I like time equals 0. And, oh look, here's a nice nifty expression. And I wanted to solve at 2 seconds, so I plug in 2 seconds into that, and you get 8 meters per second. Again, look, the seconds from t cubed and the seconds down here cancel out, so you make sure that your units work. Well, all but one of them cancel out. If we plug this in to our average acceleration formula, we get 4 meters per second, which is exactly what happens if we use the constant acceleration formula. See, it's the same. Same answer. So you can do it either way. I hope this helps. I look forward to seeing you in class.